Yeah, this is graphing square root and cube root functions. Our learning objectives to graph square root and cube root functions. Alright, so this is what a square root function looks like in terms of the algebraic sense. We're going to actually make it in terms of graphical sense. The thing you need to know is the different parts of it, and the graphing up to this point has been very similar. So I'm going to go through this relatively quickly because a lot of these are similar, and if you have practiced them, this should just be the next step. If you have not, you need to go back and revisit all of the other graphing that we've done from first semester and second semester. I know that sounds like a lot, but we're almost done with this year. So in this case, this is going to be a vertical stretch if you have a bigger number A, or a compression, a vertical compression, which is going to be a smaller number A. It's very similar to absolute value and also to a parabola as well. So this part here also gives you a reflection across the x-axis. So right-hand behavior, if the A is positive, will go up into the right. Your right-hand behavior, if A is negative, will go down into the right. And you'll see what I mean when we do more examples of this. So your parent function is always going to be whatever the A value is times the square root of x. Your h is going to shift it horizontally, so left and right. So positive is going to be left, negative is going to be right. Remember, this is the opposite one, just like in other graphs. And k is going to shift it up or down. The other thing to note is that your k is always going to be what your range, in this case, is based off of. And that's been like that for a few other of our graphs as well. But remember, this is range based. Okay. So, and when I say range, I mean domain versus range. So we're going to do the parent here and see what the parent actually looks like. In every single one of these, what you want to do is you want to use the exact same x and y values. And the exact same x and y values are going to be perfect square roots. So for example, I'm just going to have 0, 1, and 4. So 0, 1, and 4 is going to be my perfect square roots. You can do more if you would like. It's up to you. But basically what you're doing is you're plugging in 0 into the square root function, and you get 0. Square root of 1 is 1. Square root of 4 is 2. Like I said, the parent function is always going to be using these values. So when I plot these points, I get 0, 0. I get 1, 1. And I get 4, 2. And just because I'm going to do a dotted line with this, because that is, I'm sorry, this is a solid curve, I should say, and that is because it is the parent, and I call this the eyebrow function. The reason is because if you look at your eyebrows, that's kind of what one of your eyebrows looks like. So domain for this is a little tricky, so you need to kind of look at what is underneath the square root, and whatever is underneath the square root, in this case x, has to be greater than or equal to 0. So in this case, we don't have to do any algebraic stuff, so that means my domain is going to be from 0 to infinity. My range is whatever I'm adding to my k value. Here we have 0, so my range is always going to be from 0 to infinity. Domain and range, this is something I've been trying to emphasize throughout the entire semester. Remember, domain is all set of x values. And x values, you have to look at the graph and see what x values you can plug in. There are no x values over here that you can plug in, so that's why it's from 0 to infinity. But it does include 0 because of that point right there. And the range is all set of y values. Remember, that's the y values, and we only have the y values that are up here. And yes, I'm including this because these are y values that are over here, not x values. So we are basically above the y-axis, or I'm sorry, I should say the x-axis, which is going to be the line y equals 0. So that's going to be your asymptote in this case. You don't have to know that for these, but anyway, the part here is basically going to be pertaining to the range. Okay, so how does this get slightly harder, slightly more challenging? So we have our parent function here. We have is 2 square root of x. So 2 square root of x. Remember, we don't worry about this part because that's the shifting. So then what we do is we take our x and y values, so x and y values, and remember we have 0, 1, and 4. You can do 9 if you want, you can do 16 if you want, but those tend to be off the graph sometimes. So now here, this is where you need to be a little careful because when you plug this in, you get 2 square root of 0, which is 0. 2 square root of 1, well, square root of 1 is 1, times 2 is 2. 2 square root of 4, well, what square root of 4 is 2? 2 times 2 is 4. So I'm going to plot these points. I have 0, 0, I have 1, 2, and I have 4, 4. And this is going to be a dotted because we are going to actually shift this. So that's my dotted eyebrow, and I put my arrow on it. That's going to be important. Now, the thing you have to look at, again, before we do domain and range, is you have to look at where you shift. So here, I am shifting to the right 3, and here I am shifting up 4. At this point in the semester, you should be really comfortable with the shifting because we've been basically doing it with all of the graphs that we have done up to this point. So I'm going to go to the right 3, which brings me to right here, and then I'm going to go to the up 4, 1, 2, 3, 4, which brings me right here. So now I can actually fill this in as a solid curve because now that is actually my graph. You do not have to keep the parent function if you do not want to, but you need to make sure you have the solid curve as the actual function. Domain. So this, I'll color code this. It's whatever is underneath the square root. You cannot ever have a negative under a square root. So in this case, your x minus 3 value has to be greater than or equal to 0 because you can never have a square root that's negative. So if I do this, I add, I get x is greater than or equal to 3. That means my values have to be 3 to infinity. It does not include infinity, but it can equal 3. My range is going to be looking at whatever this value is. And you look and see what the graph does. You have to look and see. So I have my range, my y values are going to go from this line to above this line. So that means basically from 4 to positive infinity. It will include 4, but it will not include positive infinity because that's impossible to get to. So this part here is always going to be in relation to whatever the range is. But you have to see what the graph does because sometimes if I put a negative in front, it can flip it, and that's pertaining to your other parts that we have. So, okay, so that is square root function. Yeah, so this one's going to be a little different and involves, instead of doing square roots, you're going to do cubic roots. So first and foremost, we have your a, that again is going to be vertically stretching if the number is bigger, compressing if the number is smaller. You also have to note that if you have a reflection across the x-axis, your a, if it's positive, your right-end behavior is going to go up and to the right and down and to the left. Your negative a, right-end behavior is going to go down and to the right and up and to the left. So it kind of switches. So in this case, your parent function, again, the exact same mentality. You have your a, cube root of x, because as always, that's going to be your parent, and you're going to shift it from there. And you shift it, again, horizontal, left and right, and this is the opposite one. And then your k value is going to be a vertical shift up or down. Now, the thing that's going to be interesting about this and kind of nice about this is the domain and range is very easy. So the one that's tricky is the square root function. All right. So here is your parent, and in your parent, again, you're going to have the exact same table. And you have to make sure you memorize this because the perfect cube roots are going to be -8, -1, 0, 1, and 8. those are going to be the perfect cube roots that you have. Because what is the perfect cube root of negative 8? Well, it's negative 2. You plug that into a calculator, you can see that. Square root of negative 1 gives you, or a cube root of negative 1, I should say, should be negative 1. Again, if you think about it, negative 2 times negative 2 times negative 2 gives you that negative 8. That's the definition of cube roots. So just so you know, that's a little mini proof right there. Cube root of 0 gives you 0. Cube root of 1 gives you 1. Cube root of 8 gives you 2. All right. So now we have negative 8, negative 2. We have negative 1, negative 1. 0, 0, 1, 1, and 8, 2. So this one, like I said, is a little on the funky side. You kind of had the eyebrow type thing going here, but you also have the reverse or flip of it that's going here. So this kind of looks like I don't know, a snake or something like that. You know, however you want to think of it. So, but in this case, we don't have any shifts left or right or anything like that. And domain and range is very easy because domain is going to be negative infinity to infinity. There are no restrictions. There's no things that cannot happen. And range is going to be negative infinity to infinity as well because there's no restrictions or asymptotes that we see. So this is going to be your final answer. And all of these are going to be based off of this graph. Okay, so here's your next one. So again, you're going to be using the exact same table with this, negative 8, negative 1, 0, 1, and 8. And in this case, now my parent is going to be, remember the a, which in this case is going to be negative cube root of x. So that's this part right here, and that's from the notes slide. And again, remember what the negative does is actually going to flip it, and it's going to flip it across the x-axis. So we should have something that basically looks almost like the opposite of what we just had. So let's look and see. So I'm going to show you a little bit of a trick here. So what I'm going to do first is I'm going to have negative cube root of x, or I'm sorry, I'm going to say positive cube root of x. In this case, negative 8, which gives me negative 2. Just watch what I do here. So we have cube root, negative 1 gives me negative 1. Cube root of 0 gives me 0. Cube root of 1 gives me 1. Cube root of 8 gives me 2. Now, this is the kind of cool thing about this. What you can do is just worry about the negative at the absolute end. And the way you do that is you just take the opposite of what your y value is. So instead of having negative 2, you're going to have positive 2. Instead of having negative 1, you have positive 1. Instead of having 0, you have, 0. So that doesn't change. 1, you have negative 1. 2, you have negative 2. So what you'll see, remember the parent that we had looked like this. So this is what the parent had, and I'm not going to fill this in with curves. But this is what the shift or the flipping does. So instead of having negative 8, negative 2, you have negative 8, positive 2. So it basically flips it along the x-axis. Instead of having negative 1, you have negative 1, positive 1. You still have 0, 0, so those overlap. You have 1, negative 1. You have 8, negative 2. And you have that kind of backwards snake thing going on. Okay, so I'm going to erase these just because you don't need them. It's just kind of for a visual reference. But now, when you have this, you have to do your shifting. So your shifting in this case is going to be right 2. Your shifting here is going to be down 3. So I'm going to grab this and I'm going to shift this to the right 2. So 1, 2, that shifts me to about there. And then I'm going to shift it down by a factor of 3. So each one of the points down by a factor of 3, which gives you right here. And that's done. That's fine. So notice I am going through these quickly, but we have had so many based off of these that you need to make sure you know how to do this, especially in higher level mathematics, because it's the same type of mentality when you do this. Domain and range is the exact same for this. Remember, in the square roots, that's where you have to actually think a little bit. So, but here, you do not have to think very much for domain and range. And this is done. In class, we will get a lot more examples with this, but this is just kind of introducing the theory and like that. So.